We've had quite a lot of energetic perturbations over the past few days.
Scientists say it was the strongest solar flare of the year.
Parts of Japan's Pacific coast are being told to evacuate.
Sun is playing a significant role in a lot of these situations.
Magnitude 8 earthquake.
It was an X 5.1 class event.
The sun's whisper before the shake. What if the next great earthquake isn't coming from deep within the earth, but from the sky above? What if every tremor, every rumble beneath our feet begins not in the crust, but in the burning heart of the sun 150 million kilometers away? It sounds impossible. The sun doesn't make the ground move. Or does it? Because right now, scientists are quietly watching patterns unfold. Solar storms intensifying, magnetic fields twisting, and Earth's crust showing signs of pressure building in unusual ways. And some of them believe the next magnitude 8 or higher earthquake could be connected not to what's happening under the ground, but to what's happening beyond our atmosphere. This isn't science fiction. This is the story of a growing theory that could change how we understand both earthquakes and our relationship with the sun itself. The strange connection between solar storms and earthquakes. For over a century, scientists treated earthquakes as purely geological, the product of tectonic plates grinding, slipping, and releasing built-up stress. But what happens when the patterns don't match? There have been times when the planet shook without warning. Fault lines that were quiet for decades suddenly ruptured. Not after heavy rainfall, not after pressure changes, but right after something strange happened on the sun. In 1859, the Carrington event, the largest recorded solar storm, unleashed electromagnetic chaos across the planet. Telegraph systems sparked, auroras danced over Cuba, and compasses went mad. But lost in the historical noise was something else. A sudden spike in minor seismic activity over the following weeks, from Chile to the Himalayas. It could have been a coincidence, but then it happened again. In March 1989, another solar storm, smaller but still powerful, hit Earth's magnetic field. Within 24 hours, the Loma Prieta region of California recorded a cluster of microquakes. 6 months later, in the same fault zone, the 7.1 magnitude Loma Prieta earthquake struck during peak solar activity. Coincidence again? Maybe. But as decades passed, scientists noticed a pattern they couldn't ignore. The most intense earthquakes, magnitude 8 and higher, seemed to cluster around peaks in solar cycles. The physics of a cosmic chain reaction. So how could light and plasma from the sun possibly shake the Earth? The key lies in electromagnetism, the invisible web connecting the sun, space, and our planet's molten heart. When the sun releases a coronal mass ejection, or CME, it hurls billions of tons of charged particles through space. When those particles strike Earth's magnetic field, they compress it, like pushing against a flexible shield. That compression doesn't stop at the upper atmosphere. It ripples downward, inducing electric currents in the crust and oceans. Scientists call this geomagnetically induced current, or GIC. These electrical surges can reach hundreds of volts per kilometer, enough to fry transformers, disrupt pipelines, and even alter the stress distribution of the Earth's crust. Picture it like this. The crust is already under enormous tension, like a loaded spring. All it takes is a small nudge, a microscopic trigger to release that stored energy. Now imagine a global-scale electromagnetic pulse flowing through fault zones already on edge. A change in electrical charge, a sudden expansion of conductive minerals, and the balance tips. The spring releases. That's the theory. And though not every scientist agrees, the evidence is piling up fast. The data that made them stop laughing. In 2023, a study from the National Institute of Geophysics and Volcanology in Italy made headlines quietly, but its implications were massive. Researchers analyzed over 20 years of solar and seismic data. They discovered that large earthquakes, magnitude 7 and above, occurred within 24 to 48 hours of strong geomagnetic disturbances, 3 times more often than chance would predict. In simple terms, when the sun's magnetic field hit Earth hardest, the crust responded violently. Another team in Japan found a similar pattern. They tracked ionospheric activity, the layer of the atmosphere charged by solar radiation, and discovered that anomalies in that layer often appeared just before major quakes, like ghostly warnings written in plasma. In 2011, days before the catastrophic Tohoku earthquake, satellites detected a sudden spike in electron density above the region, a signal eerily similar to what's seen during solar storms. Coincidence? Maybe not, because those same electron spikes appeared again before the 2015 Nepal quake and again before the 2017 Mexico quake. At first, geologists dismissed it as atmospheric noise. Now they're not so sure. How the sun charges the Earth. To understand why this might happen, we need to think of Earth not as a static rock, but as a giant battery. The core generates a magnetic field. The ionosphere above holds an electric charge, and the crust, filled with conductive minerals and fluids, acts as a bridge between them. When solar particles crash into our magnetic field, they don't just create auroras, they set off global electrical tides. These tides subtly shift the potential difference between Earth's interior and the upper atmosphere. Think of it as stretching the skin of a drum. The drum doesn't burst right away, but the tension changes. And when it's already tight enough, one more vibration, one more electric pulse can make it snap. That snap is what we feel as an earthquake. This theory isn't new. As early as the 1960s, Russian physicist Alexander Chehevsky proposed a link between solar activity and seismic behavior. He was ridiculed then, but modern satellites, AI data analysis, and global monitoring systems are finally catching up with his ideas. Today, scientists like Dr. Sergei Pulanets of the Russian Academy of Sciences argue that the sun doesn't cause earthquakes directly, but it acts as a trigger for faults already near their breaking point. Signs that something is building. Now, in 2025, that theory is becoming harder to ignore. We're entering the peak of solar cycle 25, one of the most active in recent memory. In just the past few months, we've seen multiple X-class solar flares, record-breaking auroras visible near the equator, and dramatic fluctuations in Earth's magnetic field. Satellite systems have logged geomagnetic disturbances stronger than any since 2003. Power grids across Scandinavia and Canada reported surges, and seismologists have quietly noticed something eerie: a global increase in mid-level seismic activity, magnitude 5S and 6S, spiking in sync with solar storms. Could it be random? Of course. But when patterns repeat across continents and decades, coincidence starts to sound like denial. In early 2025, an analysis from the European Space Weather Institute suggested that if current solar intensities persist, the likelihood of a major earthquake event, magnitude 8 or higher, increases statistically by 40% in the next year. No one's saying the sun will cause it outright, but the message is clear. The conditions are aligning. The crust under pressure. Tectonic plates don't just slide. They store centuries of energy. When solar-triggered currents run through conductive rocks, especially in fault zones rich in quartz or fluids, they generate heat and pressure. A 2022 Chinese study simulated this effect in a lab. They exposed granite samples under stress to pulsed electromagnetic fields. Within minutes, the microfractures widened, and small-scale slips occurred, tiny lab quakes. Scaled up to the Earth's crust, that's the difference between a silent fault and one ready to rupture. And where could that happen next? geologists point to three potential zones: the Pacific Ring of Fire, the Himalayan Belt, and the Cascadia Subduction Zone off North America. Each is overdue for a magnetic 8 or larger quake. Each is located under regions currently recording geomagnetic turbulence. In other words, the perfect storm is forming both above and below. The unsettling precursors. Before many major quakes, something strange happens. Animals act restless, compasses drift, and air ionization increases. In 2010, hours before the Chile earthquake, scientists detected a spike in ground-level electromagnetic noise. Similar readings occurred before the 1999 Izmit quake in Turkey. In both cases, the geomagnetic field had been disturbed by solar wind the day prior. If the connection holds, these electromagnetic precursors could become the next frontier in early warning systems. Imagine a world where space weather forecasts include seismic alerts, where satellites tracking solar plasma can give us days, maybe even weeks of warning before the ground moves. That's what researchers are racing to develop: a solar seismic model capable of predicting quakes not by the sound of the Earth, but by the hum of the sun. The science of doubt. Of course, not everyone is convinced. Traditional seismologists argue that the data correlations are statistical artifacts, random alignments in noisy datasets. They point out that earthquakes occur every day somewhere on Earth, and that solar storms are frequent enough to overlap with some of them purely by chance. And they're right. Correlation doesn't prove causation. But the growing body of research suggests something subtler. Solar activity doesn't create earthquakes everywhere. It simply tips the balance where the crust is already stressed. That's why the connection isn't universal. It's selective, conditional, and rare. But when it does align, the results can be catastrophic. The pattern of history. Look back over the last century, and a strange rhythm appears. The 1960 Chile earthquake, 9.5 magnitude, occurred at the peak of solar cycle 19. The 2004 Sumatra Andaman earthquake, magnitude 9.1, struck as solar cycle 23 approached its maximum. The 2011 Tohoku quake coincided with a surge in solar flares after a quiet minimum. Each of these events aligned within months of intense solar disturbances. Now, in 2025, solar cycle 25 is surpassing predictions, producing double the expected number of strong flares. The timing echoes those historic peaks almost eerily. Could we be standing on the edge of another global-scale rupture? No one can say for sure, but history has a rhythm, and right now, it's beating in time with the sun. The Emerging Warning Network. Around the world, small groups of researchers are quietly connecting the dots. In Japan, space weather scientists are working with seismologists to build dual monitoring models, tracking solar wind speed, geomagnetic stress, and crustal pressure together. In Italy, AI algorithms scan for anomalies in satellite ionospheric data, patterns that precede quakes. And in the US, NASA's magnetospheric multi-scale mission is providing real-time readings of how charged particles interact with Earth's magnetic field, giving new insight into how those energy surges might cascade into the ground. If they're right, the next generation of earthquake prediction might not come from fault-line sensors, but from space probes orbiting the sun. When science meets the unknown. Even with the data, the physics remains murky. How exactly does a geomagnetic pulse translate into rock movement? Why do some regions respond while others stay silent? The answers might lie deep underground, literally. Researchers studying conductivity maps of the mantle have discovered vast regions of molten, iron-rich rock that could act like electrical wires connecting surface faults to Earth's interior. When solar energy hits, those wires could channel current, heating fluids and destabilizing fault systems miles below. It's as if the Earth itself becomes part of a massive cosmic circuit, and when the current spikes, the weakest links give way. It's not mystical, it's physics, and if we can understand that circuit, we might one day control or at least anticipate it. Are we ready? Preparedness remains the weakest link. Most countries still base earthquake readiness solely on geological models. If this solar link proves true, entire monitoring systems will need an upgrade. Satellite coordination, geomagnetic observation, and predictive AI trained on solar activity cycles. The stakes are enormous. A magnitude 8+ quake today in a populated region, Japan, the US West Coast, the Himalayas, could affect tens of millions, cause trillions in damage, and set off cascading disasters from tsunamis to infrastructure collapse. But if we can even predict it a few days earlier, millions of lives could be saved. That's the hope driving the research. That's why this isn't pseudoscience, it's persistence. The quiet concern among scientists. In closed-door briefings, scientists are discussing something they rarely do in public: the possibility of a solar-triggered megathrust, not as conspiracy, but as risk assessment. When solar storms strike, magnetometers on Earth detect brief oscillations, tiny wobbles in the planet's magnetic field. Recently, those wobbles have grown stronger and more frequent, and every major quake in the last 2 years has occurred within days of such an event. It's not proof, but it's enough to make even the skeptics pause. As one researcher put it, if the sun really can pull the trigger, we're not just watching the sky for weather anymore, we're watching it for earthquakes. The cosmic clock. Every 11 years, the sun completes its magnetic reversal. Its north and south poles flip. This is the solar cycle, and it governs everything from auroras to radio blackouts. But as it turns out, it may also govern how and when the Earth shakes. When the sun's magnetic field flips, the heliosphere, the bubble of plasma around the solar system, ripples. Those ripples change how cosmic rays hit Earth, how our magnetic field bends, and how internal electric currents shift. Each cycle is like a clock, and we're approaching midnight. If past patterns hold, the peak years following this flip will be marked by volatility, in the sky and below the ground. And for scientists, that's both terrifying and fascinating. The new frontier of Earth science. The real revolution here isn't about fear, it's about understanding. We're realizing that Earth isn't an isolated system. It's part of a living network, a cosmic feedback loop between the sun, space, and the solid ground we walk on. Lightning doesn't stop at clouds. Winds don't stop at the atmosphere. And quakes, perhaps, don't stop at the crust. They're all connected by invisible currents, and those currents start with the sun's heartbeat. That heartbeat is quickening. The warning and the hope. Right now, scientists aren't predicting a specific earthquake. They're watching the signals: solar wind velocity, magnetometer spikes, atmospheric ionization. The signs are subtle but unmistakable. The planet is under tension. We can't stop it, but we can prepare. The research being done today could soon allow us to forecast quakes with the same confidence we predict hurricanes. And that's the transformation worth believing in. Because if the sun truly holds the key to understanding Earth's most violent moments, then maybe, by studying the stars, we can finally learn how to protect the ground beneath our feet. A cosmic whisper. The idea that the sun could trigger earthquakes once sounded like myth. Now it sounds like physics we're only beginning to understand. Every magnetic storm, every flicker on the sun's surface might be part of a larger conversation. A cosmic whisper that Earth answers with a tremor. The next magnitude 8+ quake could still come from deep within. But maybe, just maybe, it will start with a pulse from the sun. And if that's true, then our planet isn't just turning under the stars, it's listening to them. The sun speaks in plasma and light. Earth responds in waves and motion. And between them lies the fragile layer where we live, feeling the rhythm of both worlds, the heartbeat of the sky and the breath of the ground. Stay blessed and stay curious.